Section 10.4 concerns the difference of proportions. We're in this kind of situation now. Let us continue using mu even though we are considering the proportions. Mu is for population's proportions, and consider mu delta as a difference, and we can estimate those using the sample proportion P1 bar, P2 bar, and the difference between those two. Real purists may prefer to do something like this, using pi as population's proportion, and pi delta is pi 1 minus pi 2, and pi 1 is estimated by p1 bar, and so on and so forth. But I've never seen a student feeling comfortable with these because pi was usually reserved for something else. So I'll continue using mu's even though we are not doing population mean anymore. As for the standard errors, we have the same relation as before. Pythagorean identity, SE squared is equal to SE1 squared plus SE2 squared. So we have this result after taking the square root. Now, something further. What is SE1? They're coming from proportion, isn't it? And the standard error formula for proportion is, well, P1 minus P over N, or square root of that. So this one corresponds to SE1, and that thing corresponds to SE2. And we have the square root and squared, so cancel each other out, and we may end up with the final formula down here. And if you prefer to use this final form, please go ahead and use it. I usually do it like that because I'm comfortable with all kind of algebraic manipulation. But if you're not really comfortable, just do it as before. Calculate SE1 and SE2 separately and go from there. What am I talking about? Let's go to this example. 4.3. In studying his campaign plans, Mr. Morris wishes to estimate the difference between men's and women's views regarding his appeal as a candidate. A sample of 1,000 voters were taken from each population. It was found that 388 out of 1,000 men selected and 459 out of 1,000 women selected favor Mr. Morris. Find a 99% confidence interval for the difference. Well, observed proportion for men is 388 over 1,000, so 0.388 or 38.8%. And for women, it is 0.459 or 45.9%. And the difference will be easy to calculate. And here it is. The difference is 0.071 or 7.1%, if you will. How about the standard error computation? Here we go. This is a standard error computation for women. P times 1 minus P over N, or square root of that, and square again. We have that. And this is standard error computation for men. P 1 minus P over N, square root and then square cancel out. So we have that one. So we have this. Add them together and take square root, and we have this result. So that is a standard error. And then what do? We have to find out the 99% confidence interval using the z-table. So here we go. N minus center over standard error is equal to the z-score. And z-score associated with 99% confidence is approximately 2.58. But I use a little bit more precise figure using Mathematica, 2.5758 or something like that, plus or minus of that because of the symmetry. So we have this result for lower end and that result for the upper end. And then the difference between women and men's is between 0.0142 to 0.127 something, or in terms of percentage, 1.42% to 12.78%. Excuse me, 1.42 percent point and then 12.78 percent point. Not percent, excuse me. I should have said percent point. Well, on second thought, decimal looks a lot better solution. The percentages can be a little bit confusing. So I should have specified percent point here and percent point there. And this one over here, 99%, this is really percentage. This is confidence level, not the difference. So no point there. Really, I'm beginning to appreciate decimal form far more than before, because this percent versus percent point can cause confusion. Anyway, here's a visualization. We are in this kind of confidence interval. 0.071 goes right in the middle, 99%, the blue part in the middle, and 0.005 there in the left hand side, and 0.005 in the right hand side. Okay, that was simple. And let's go over to hypothesis testing example. How about the next problem here? A salesperson for a new manufacturer of a cellular phones claims not only that they cost the retailer less, but also that the percentage of defective cellular phones found among the products will be no higher than the percentage of the defective found in a competitor's line. To test this, a random sample of 150 cellular phones from each manufacturer selected. And then we have something like that. Salespersons, 15 defective out of 150. Competitors, 6 defective out of 150. Can you reject a salesperson's claim at the level of significance of 0.05? Well, the salesperson claimed that certainly they're cheaper, yes, but this one is not about cheap. It's about defective. As for the salesperson claimed, yes, no higher percentage of defective found than competitor's line. So about the same as no difference. That's basically the salesperson was trying to claim. And does it look like really no difference? 5 out of 150 versus 6 out of 150. Looks like salesperson's cellular phone line has more defective. So null will be no difference, and then alternative hypothesis will be bigger than that. Kind of like this here. About the same as 0, that's null, and then difference is significantly greater than 0. That's going to be the hypothesis. Now how about the sample statistics? Some are straightforward, some require a little bit of thinking. These are all straightforward. 15 out of 150, 6 out of 150, so the difference is 0.06. That's the number that you're going to use at the very last moment. And the sample sizes are the same. And how about the standard error? Well, here I decided to use a formula there, I think. Instead of calculating SE1 and SE2 separately, I just used the final formula here. That's okay too, that's actually a shortcut. And run your calculator, and then you end up with 0.029 something. That's gonna be the denominator. If you draw a picture, it's gonna be kind of like this. Well, okay, turned out that I ended up giving away too much. Please pretend you didn't see the 0.06. So 0 goes right in the middle, and we want to find out the critical value, which we don't know yet. Turned out it is 0.048, but pretend you didn't see it yet. Okay, that's the scheme. And let's set up and let's find out this critical number. How do I do that? N minus center over standard error is the t-score. So this x minus 0 over SE is appropriate score. As a matter of fact, there is a t-score. It should be z-score, excuse me, because this is a proportion. So looking at the z-table for 0.05, you get 1.65 approximately speaking, or here's a little bit more accurate figure using mathematical, 1.64485. And setting up this equation, you can solve for x. What you get? 0.048 something. And that happens to be a critical point here, 0.048 something. And 0.06 is definitely in the red region. It's bigger than the critical point. So is it too far away from the null, or is it close enough from the null? Too far. It's in red region. So the alternative hypothesis wins. We reject null and accept the alternative hypothesis. In other words, the null hypothesis is just accepting the standing claim in this case by the salesperson. An alternative hypothesis wins, which means more defective. We have a little bit of time left, so let's do the same thing using the probability value approach as well. And here is the setup. The difference between the population mean will be about the same, and difference will be bigger for alternative hypothesis. And in this case, you just draw a normal picture with observed difference of 0.06, and then find out the probability to the right hand side, the wing here, greater than 0.06, that one. And if this probability is greater than alpha value, then the probability that null is correct, roughly speaking, is greater than threshold value alpha, so null wins. And in this case, the probability is too small, so the probability that null is right is not large enough. So null is out and accept alternative hypothesis. That final interpretation can be a little bit tricky. And how do we actually find out the probability? You can look up the z-table, which I'm showing right now. You have to calculate the z-score kind of like this, n minus center over standard error, and n is given as 0.06, center is 0, and standard error we calculated. We end up with z-score of 2.05 something. So look up 2.05 from the z-table. Let me show you. Let's go to the second page. 2.05. 2.05, you get 0.9798. So subtracting 1 and 0.9719 from 1, you get 0.02 something, and that's less than alpha value. Consequently, we reject null and accept alternative hypothesis. It is easy to calculate the red area because you can easily find out the z-score, but final interpretation can be a little bit tricky if you're not really used to this probability value approach. I don't usually like to use this approach because it's less intuitively clear than critical value approach, where you can clearly see that observed value is too far away from the null, as you can see here, or close enough to null, going to blue region. But if you prefer probability method, go ahead and use it. I wouldn't stop you.